Assalamualaikum and good day everyone. Today our group will present a critical literature review of the paper titled Experimental and Numerical Evaluation of Nano Enhanced Phase Change which materials which is and EPCMs for thermal energy storage in solar collector systems, published by Zhao and colleagues in 2022 in the Journal of the Renewable and Sustainable Energy Reviews. In computer engineering, the global shift toward sustainable energy makes solar thermal harvesting vital. However, solar energy is intermittent, requiring efficient thermal energy storage (TES). Phase change materials like paraffin wax store energy at high density during melting, but their low intrinsic thermal conductivity, which is only 0.15 to 0.25, severely restricts thermal charging speeds. Dispersing high conductivity nanoparticles like copper oxide (CuO) into the wax creates a Nano Enhanced PCM that can solve this bottleneck. Our critic evaluates how effectively Zhao et al. Addressed this challenge. Moving to the next summary, Zhao et al. Evaluated the thermofluid performance of CuO nanoparticle is dispersed in paraffin wax within a flat plate solar collector using a hybrid approach. Experimentally, they tested 0.5 volume to 1.0 and 2.0 volume concentration on a bench scale collector with thermocouples and data acquisition. Numerically, they ran computational fluid dynamics simulation using ANIS fluent with an enthalpy porosity formulation. Their results show that adding 1.0 volume CuO increased thermal conductivity by 28.4%, reduced melting time by 31.2%, and boosted daily collector efficiency from 48.5 to 61.2%. However, exceeding 1.0 volume caused particle agglomeration and settling, suppressing natural convection and dropping performance back to 53%. Thus, 1.0 volume percent was identified as optimum threshold. Now, let's critically evaluate the paper's scientific communication and methodology. First, research question is exceptionally clear and well justified. The authors explicitly asked, to what extent can CuO nanoparticle concentration improve heat transfer kinetics without reducing natural convection during phase change? Regarding methodology, we identified both strength and weakness. A clear strength was their experimental rigor using ultrasonication and CDS surfactants to ensure stable dispersion. However, a key weakness in their CFD model was treating the fluid as a single-phase homogeneous continuum, and EPCMs are multi-phase fluids where particle interaction, Brownian motion, and thermophoresis alter viscous drag. Furthermore, using a constant heat loss coefficient oversimplifies transient ambient environmental fluctuations. Regarding data validity, the numerical predictions align well with experimental results during early conduction dominated melting. However, an 8.5% variance occurred late in the melting phase because the single-phase CFD model underestimated buoyancy-driven natural convection. The authors rightly highlighted a critical fluid dynamics trade-off. Higher nanoparticle loading increased dynamic viscosity. At 2.0 volume percent, the viscosity rise suppressed natural convection currents, counteracting the thermal conductivity gains. For limitations, the paper openly acknowledged short experimental windows, testing only 50 charge and discharge cycles, and noted nanoparticle precipitation over time. However, they failed to analyze long-term thermomechanical degradation, chemical compatibility over hundreds of cycles, or economic viability for commercial scaling. Despite this limitation, the paper holds significant engineering value. Defining the 1.0 volume percent parametric threshold gives a clear design guidance to HVAC engineers, solar collector manufacturers, and waste heat recovery system designers, preventing costly over-investment in nanomaterials. Ethically, the paper contains original empirical data without evidence of manipulation, selective reporting, or plagiarism. No human or animal subjects were involved, and conflicts of interest were properly disclosed. In conclusion, Zhao et al. Deliver a valuable, reproducible contribution to thermal fluid engineering by bridging material science and mechanical system design. Thank you for listening.